Good morning. I'm Barak. I'm a software developer, full stack, based in London. I do consultancy for small startups who need to get a lot of juice out of their systems. And this is what we're going to be talking about today. We're going to be talking about high-performance GraphQL through an introduction into GraphQL, what it means for React developers. This is what we're talking about today. And exploring some underlying performance optimizations and trickery with JavaScript and how we can write better systems overall. So right off the bat, before we start, you might be wondering why we're talking about GraphQL. This is a React conference. But I think it's important to talk about it for two main reasons. One is the evolution of the web over the last, I'd say, 5-6 years. Going from, as front-end developers, which I guess most of us are, if not full stack, up until, it's not long ago, if we talk about the grand scheme of things. Front-end used to be rendering templates, rendering HTML, rendering CSS, maybe doing a bit of JavaScript for interaction. And over the last few years, with front-end MVC frameworks becoming more popular, and with Backbone having its time in then Angular, and now Angular 2 and React, front-end developers get more and more ownership over the application itself. To the point where the bulk of the application today for many web applications is in the front end. And the back end is left responsible for providing APIs, for providing data and supporting our front end applications. But we are the ones responsible for business logic. We are responsible more and more for application performance and maintenance over time. And that's why I want to talk about GraphQL and in new and interesting ways that you can deal with data in your applications. So starting with React, let's look at a very simple example of rendering a list. Rendering a list of users and their friends and the events that they're attending. Let's say it's a social feed on Facebook or any other social network. Maybe we have some data. Maybe it's coming from a network request. Maybe it's local. And let's say that we have an array of objects, and I have my name, and I have my friends, and I have the events that I'm attending. And I might have a list, and I might have a user component, a React component, and I can map all of my items in my data list into instances of that component. And a user can contain other components. It could contain friends or events, and we can have a lot of different levels of data nesting within a single component. Now, when we look at a list like this with users and their friends and their events, it's pretty straightforward thinking about it from a React perspective. But where does the data for that part of an application comes from? If we're looking at the way many applications are built today, you have two options. And most of them fall under the category of RESTful APIs. Your typical HTTP network requests. If you make the very strict form, typical format of a RESTful API, you'll probably have an API/users, and you can give it an ID, and you'll get the first user. Let's say I'm user number 1, and I'm getting the user record. I'll probably get a JSON back. And to get my friends, I might have to go into /friends to get the friends of that user, another level down the API, and the same for events. And that means I'm making 3 different network requests to get the data for a single component, for a single view of my application. The other option is saying, well, whatever, I'll have a custom API, this is internal, I can do what I want, and I'll have users 1, and I can maybe include what else I want in that object. Maybe I want my friends and events, and I can just have a big join query, very efficient, just do it in one go. But both of these methods have a few problems, typically 3 problems I want to talk about. The first one is that if I was to ask any one of you what's the data structure behind these APIs, there's absolutely no way of knowing. The data format behind an API is implicit. All you know is that you hit this API, user/1, and something comes back. Hopefully it's JSON, hopefully it's in a format that I can consume, and it's in a way that wouldn't take too much processing. But to understand the data that comes back, maybe I'll have to make a request in Postman or in the console, I'll see what I get back. Maybe I'll have to read documentation. Maybe I'll have to go to other examples of code or read the source code for this API. So this API is implicit, and there's a block between me and understanding what I'm getting back. And it's not very descriptive. The other problem is that I need, for one of these options, I need to make 3 different network requests to populate a single component, and that's unnecessary. Or I have my own proprietary API. And there are 2 problems with having proprietary APIs. If you're doing web, and most of us, I guess, do web, you don't have a lot of problems with versioning, because once a new version of your application is out, all you need to do is refresh the browser, and everything's done. Your project is always up to date, and your new APIs will be used. But let's say you're building React Native or React Native Desktop for Windows, and you're baking your APIs into the application. And you release this application on the Play Store or App Store, and now the endpoints are hard-coded. And something changed. Maybe instead of the user location in coordinates, you have latitude and longitude. Maybe you split the name into first name and last name. You can't do that on the same version of your API because all of your current apps will break. You need to deploy a new version of your API. It'll probably look something like this, v1, v2, v3, 4, 5. And you need to make sure that you correlate the supported APIs with the current versions of your app that you have out in the wild. When Facebook first presented GraphQL, they gave a statistic that they have about 100 versions of different applications that they have as Facebook out and about. And they have to support all of them because they have a support contract of at least a year of their applications. And that could be a nightmare. Imagine having 10 different versions of each application, and you have v1 and 2 and 3 and 4, and you have to support all of these endpoints. And the last problem that we have, and that is very annoying as front-end developers, is that let's say we need a bit more data for an endpoint. For a user, maybe we need, I don't know, their profile picture in a higher resolution. Maybe we need their current location. We need to ask the backend team or whoever is responsible for that API to add another key to the JSON object that we're getting back and wait for them to deploy the version, a new version of the API, and go to our project and change the version of the API that we're consuming and making sure nothing else changed or broke. And we have no control. We don't have full control over the data that we're consuming from our API. We are provided with a limited subset of APIs, and we have to use those, and we have to make do with what's given to us. The other option is GraphQL. So for those of you who don't know what GraphQL is at all, this will be a brief introduction. GraphQL is a query language, and what that means is that it's a common interface between the client and the server, between the front end and the back end, to communicate about data, about the data dependencies of your application. And what that allows us to do is to make client-specified queries, not just client-specified API requests, but client-specified queries. So if in the RESTful way we're to get a user in whatever data is inside that user, we said we hit API/user/1, whatever. The GraphQL way would be to only have a single endpoint. If you're working with GraphQL, you're forgetting about the concept of API endpoints. Instead, you're talking about queries. And this would be the query that you use. It looks a lot like JSON, and it's very readable. This is an example of asking for, I don't know if the laser works, yeah. We're asking for a user. For that user, we're asking for the name. We're asking for the friends. For each friend, we're asking for the name, the events that I'm as a user attending, and the title and the time of each one of these events. So the query, and this is written on the front end, it's not written on the back end, and I can change this and get different data. But when I look at this, I know exactly what I'm getting. I'm getting a user record with a particular ID and all the keys that will be included in that request. And that's a lot more descriptive of the data that I'm getting back. If this is the query, this is the response. What you put in is what you get back. It's almost the same format. And you know exactly what are the keys, what is the structure of the data that you'll get back from a GraphQL API. So let's talk about how this magic happens, how the backend and the front end know how to communicate and they understand these dependencies. How is it that when I say username, the server knows to get the username? And that is because the underlying mechanism of GraphQL is a type system. The language provides a type system for us to declare our graph, our data graph, with nodes and connections. Nodes being types of data that we have in our application. Could be user, could be event, could be the query, which is the top level entry point into our graph, and connections between them. And we'll talk about that in a second. I just want to say, if concepts of graphs and things are scary to you, and they were terrifying to me when I first started out with this, don't be scared. In all likelihood, you're already using graphs in your applications, even if you don't know it. Anyone who's using an ORM, an object relational model, like Mongoose or any other layer of using your backend systems to map to a database, you're already using a graph. All that means in terms of our database is that we have different models, different entities in our system, and they can connect to each other with relationships. It's the way we think about SQL databases, even if they're table-based. So back to the type system, you can see that we have two main types here. We have an event and we have a user. And let's look at the user. A user would have an ID and a name, and we can see that they're strings, and we have friends and events. Now they are arrays of other types that I'm declaring. I can have a user require other users. In the case of the friend, here we go, here. And we can require other events. And we know that this event will have ID, title, time, creator. So when I'm looking at a query, both the front end and the back end know exactly what is available to me within the graph. So if I'm making something that doesn't exist, I'll just get an error, and the query wouldn't be executed. In terms of connecting React into GraphQL, you can use a library called Relay. Relay is a layer of Flux, like Flumux or Redux, that is available in React. It's another Facebook project. And what it does, it allows you to associate small GraphQL queries with your components. So you can say, this is a user component, and we won't show it. We showed it at the beginning. Let's say it's a simple React component. You can declare the data dependencies for that component using a snippet of GraphQL within your front-end code. And this is how you make network requests. You don't make API calls anymore. You declare fragments of queries from your graph, and these are queried automatically. So in this case, let's say I have a user component. I can say that this user requires the user data from the graph, and it needs the ID and the name, and I can even say I need something from another component. Let's say I have a component for a friend, and it looks a bit differently for a user because it shows a relationship when we first met, whatever. I can have that component associated with a fragment and start collecting them up. And this is how you build your graph. So again, when we look at GraphQL, it's very easy to understand what to expect from this query. And this is what it looks like on the node side. If Relay is the front-end aspect of GraphQL, how to attach these very descriptive queries to your components, this is how you build the tree in actual Node in the express reference implementation. Basically, all it is classes, and we're familiar with classes if we're familiar with extending components on the front end. All it is classes that I extend with the fields that are available on that node, on that type. So this is a user type. It would have fields of ID and name. And really, this is what we're going to be talking about today in bulk, is the connection between nodes and how we query them. So if I have friends, I'm not just saying I have another type. I'm saying I have a type of user, which I'm declaring here. It's self-referencing, which is really cool. But this is the point. I'm resolving from the user into its friends. I'm resolving from the user into the events. And what that means is when you make a GraphQL query, the first thing that happens in a query that looks like this is that I will query for a user. Again, this is just a single API call. But in the backend, what will happen is I query for a user. Once I have the user, I can populate the fields based on the type definition, based on this implementation. And I can say, OK, I can get the field ID and name directly off the object that I have, but I need to make another database query to get the friends and to get the events. And these will all be collected back into a single response. And to use it, like I said, there's only one endpoint. So we're just calling use, which is it's a Node.js or Express way of creating an endpoint or mapping to an endpoint. And we're giving it the entire schema. So this endpoint will consume your query. It will map it against the full existing schema, make all the queries necessary, and return the data back. So we're making one declarative query instead of 3 or more with the example just of user and friends and events. And I want to talk about, to me that was obviously very cool. It was mind-blowing first when I saw this, and I had to try it, and I built a project in GraphQL, and it was amazing. But there are some real-life aspects to working with GraphQL once your project starts growing, and this is what I want to talk about today. What happens on the database? Like, this is one API call, and that's great, but what happens between GraphQL and my data? So let's talk about database calls in this thing. When we're asking for, as we saw, the promises are resolved, we make at least 3 queries in this call. We make a call for the user, and that's one promise, that's one network request. And then we have another call for the friends, and we have another one for the events. So that's one query, but how many database calls are we actually making? So I want to show you a small tool that comes prepackaged with GraphQL. and that's called GraphQL. It's an interface for you to explore your schema, and you can go into the documents. It consumes your schema, so you don't have to map it again. It reads the mapping and generates this interface. And you can see that you have a query, and this is the top level entry to your graph. And within a query, I have users, and I have events, and I can click on a user, and I can see all the properties that are available within it, ID and name and friends. I can really explore the entire graph. But what I can also do is run arbitrary GraphQL queries here. So let's look at a very simple example at a query that just asks for a user. And I'll run this, and you'll see we get a small fetch user here. And these logs are in Node. I'm making a console log every time I'm actually hitting the database. So every time I'm querying a database, we'll get a line there, and we'll see when things start going sideways. So far, I need one node, one query. That's OK. We'll clear this, and we'll take a look at our query with the friends, so something a bit more nested. We're looking for a user with an ID of 1, and I want the name and the friends of that user. And I run this query, and now we get, first of all, I mean, this is awesome. We have all of the data just as the query was. We have the user and the friends, and this is great. But what I get your attention on is this. We have 2 calls to the database. So things are starting to get a bit bigger, but it's still OK. We're looking for another piece of the data. So two database queries are manageable. We ask one for the user and one for the friends. Let's look at another example. Almost the most complicated, where we're looking for friends as well. We'll clear this and run the query. And now we get, in a single response, the user and the user's friends and the user's events. And I could add a friend ID here or the event's time and date, whatever it is, and it all returns in the same response. And we get 3 database calls. But I want to show you what happens when you go one level deeper. And when I first saw this, it really freaked me out, because I saw this on a production app that was starting to get really, really slow, and I had no idea what was going on. So let's copy this query in. And this is a bit more complicated. We're asking for the creator of each event. See this here? The creator of each event, so that's a user node that's nested from within the event, and we're asking for the events of each one of my friends. So I want to see from my friends which events are going to. Maybe it's a very complicated user profile screen, and we need all this data for a single view, which is not that unreasonable. It's not that much data. And for each event, I want to know who is the user that created it. Maybe I want to show bubbleheads next to each event. Maybe I want to show attendance. And you want to show the people's names who are my friends, and I know they're going, like Facebook does. I'm going to run this thing, and this is terrible. This is really, really bad. We're making more than 30 queries to the database from something that seemingly isn't that much more complicated. All I wanted was the user who gets to this event, and this becomes a disaster. And the first time I saw this, I think, was a query, and it was making 52 database calls, and I just lost my mind, and I had no idea what was going on. And then I realized that what happens is that there's a limit to how many things you can batch with GraphQL, how many things you can group into a single joined query. So let's see what happened. Why did we go from 3 to 35? So yeah, obviously, that's a disaster. Let's look at the query chain. And when we explore the query chain in GraphQL, I'd like to talk about nodes and queries. So we enter the graph with a query, or we're saying we're looking for a user, and what are we getting back? How many nodes are we getting back? When we're looking at a user, we're making a query for a single user, and we're getting 1 node. So far, so good. Now we're asking for the events and the friends of that user. So we're entering with a single user to get their events, but we're getting e-events back. As we saw, we're making 1 request, and we're getting all of the events, or all the friends. Now this is where things start getting messy, when we want something for each one of these. Because if I want the creator of each event, now I'm making e-queries, and I'm getting back many more nodes. If I want the events of every single one of my friends, I'm making F queries. And if I want the creator of each event my friends are going to, we have the number of friends times the number of events, and we're going to make a query to the user table every single time. So this is obviously not sustainable. So one solution would be to just restrict the depth of queries and saying you can't go more than 2 levels deep, because things become problematic. But then you end up making multiple GraphQL queries for every single views. So that's not a solution. You'll end up hitting the database the same amount of times and making more network requests. So let's see how we can, but yeah, just to recap, the problem is that once you make the first join queries, because it's easy to say, I want all the friends of this user, but because of the structure of the graph, it's very difficult to say, I want the events associated with each one of the friends, because it's a promise that resolves to individual nodes. And for each node, I'm going to have a separate process. Not necessarily a certain query. We'll see how that can be done. But it's a separate process. It's a separate promise that's resolved, and it's a separate function running. As I said, once a user is resolved, it's all separate processes. You can't really build your custom function for a massive join function and do it all with one query, which might have been more optimized on a RESTful or a custom approach. So what I want to talk about is DataLoader. And like I said, this is partly sort of a React GraphQL tutorial, but really I want to explore some really interesting JavaScript techniques for optimizing problems like these. How can I handle seemingly unrelated operations in my program and optimize execution of such heavy processes like making database calls? So DataLoader is a project by Facebook. It's less popular, but it's part of the GraphQL-Relay-React family of open source projects that they've been releasing, and it addresses exactly this problem, because it's a problem that Facebook have been having as well when they started making bigger and bigger GraphQL queries, which they're using internally. So it's a tool or a library for coalescing, which is a fancy word for merging, and caching requests. So if I'm making multiple calls for the events of each one of my friends, how can I instead turn it into a single call without hacking the structure of the graph completely? How can I leverage the nature of JavaScript, which is our weapon of choice here, to do these more advanced processing operations? But before we can talk about DataLoader and before we talk about GraphQL any further, I want to talk about asynchronicity, because I really want to explore the underlying mechanisms. Otherwise, it's just a library, and you can read that in the documentation. So asynchronicity in JavaScript and how it works in the last iterations of V8 and the newest specs of JavaScript, and some things that you might have not known are possible. So we start with the call stack, which is the basics of how JavaScript operates. When we make a function call, it will be placed in a call stack. It will be placed in a frame of execution. And the frame of execution, or the call stack, is what keeps trace of all of the currently active operations within a single call. And that is how I know to return a value from a function to the function that called that function, and return to the function that called that function, all the way to the highest level of my application. So I can call console log here. You can see that I'm defining two functions, but the first thing that I'm doing is calling console log. And console log calls double if even. Double if even gets a number. In this case, it'll get 4, which will be even. And if it's even, it's calling double to double that number. So double if even is added to the stack, and then it's calling double. And then double is added to the stack. All of the synchronous calls, all of the the entire sequence of operations is added to the stack. And then it starts emptying out. Double returns into double if even returns into console log, and slowly the stack empties out, and we can have a new frame. This is how synchronous programming works. This is how synchronous JavaScript works. If I had this line written twice, it would go through this entire operation fully, complete, and only then will it be able to start a new frame of execution, clear the stack, and restart. So nothing happens while my console log is being executed, and that is the blocking nature of synchronous programming. But we know that JavaScript's top feature is being non-blocking. So how does that happen? That is the task queue. The task queue is a place where we can defer execution for later. So what does non-blocking mean? Non-blocking doesn't mean multi-threaded or parallel. It just means I can do parts of different operations at different times without having to complete a full operation before starting a new one. So that is a network request. I can start a network request, and while it's being processed in the background, I can do other stuff. It's still a single thread. There's still a single line of execution, but I don't have to complete my operation before I'm moving on to doing something else. So let's see how that works. Let's say we have a function now called double laters. And it sets a timeout. It doesn't even give it a number because I wanted to just show the nature of the task queue without actually waiting. And the same thing, console log, double if even, double. We call double laters which calls a set timeout. Now, the call to set timeout is synchronous. The allocation of the callback is synchronous. And we put this callback in the task queue. And this task queue will keep a reference of where this function was called, what was the context, part of what callback, what does it have access or not have access to in terms of the scope. And it's just waiting there, ready to be executed as intended when the time comes. And in the meantime, my call stack completed, because the callback is associated, it's not being executed yet, and this is the call stack is cleaned out. And we're waiting on the callback. This is a timeout with 0, so it will be resolved at the next available frame of execution. So now the callback becomes our new call stack. We start a new call stack from that call, but my callback might call other functions, which is what happens. Callback, which is this anonymous function, and then console log, and then double if even, and then double, and then it clears. And this is how the base of the JavaScript event loop, the base of JavaScript asynchronous model is implemented with this task queue. We can put calls or callbacks for later execution, and they will wait in the task queue until further notice. What triggers these things is the way, what's called web APIs. When a timeout is set, that's internal to the browser. When the timeout is complete, the task is marked for ready to come back to the call stack. The same is true for network requests. The browser has an internal API that resolves HTTP network requests. Once they are resolved, that task in the task queue is marked as ready, and it will become the next base for the next call stack in the next available frame of execution. And that is, by the way, the reason why timeout is not guaranteed to run after 3,000 milliseconds. It will run after 3,000 milliseconds whenever the call stack is free, and we can actually start a new frame of execution. Now, the really cool thing is that there's actually another queue that not many people are familiar with. I definitely wasn't familiar with until I read through the source code of DataLoader. And that's the job queue or microtask queue. And it's another part of the asynchronous model that is only now being implemented in Chrome, but is already implemented in Node and is available for us to use. And it just sits there. And on the face of it, it just seems like, why do we need another queue? But let's look at this example of another function that's called doThing. And it sets a timeout, and it resolves the promise immediately. When you resolve a promise immediately like this, it's synchronously resolved and immediately ready for calling then. So you can immediately, it won't be immediately, will still be asynchronous, but you don't need to wait for an operation to complete. It's like a network request that resolves immediately, automatically, with whatever data you pass in X. That will be the value that the first thenable will get. So let's say we're calling doThing. So we're starting our synchronous call. We're scheduling a timeout right here to call an alert with the number later on. And we're resolving a promise. These are the only synchronous operations so far. And then we set the callback. But the thens for the promise, the thenables, the callbacks for then and catch for handling promise resolution are placed elsewhere. And that is also true in Chrome today if you're on the latest version. They're placed in another queue, in the job queue or microtask queue. And then the stack clears, and you would expect that once the stack clears, the first thing to jump back into the call stack would be the timeout, because it's the first one that is put in the queue. It has priority. It's within the task queue, the order is by insertion. So if you have multiple timeouts set to 0, the first one will be the first to resolve. But no, the first then is the one that's resolved, the one here calling double if even. And then we get all this thing. And then the second then is resolved with console log. And only then, once the promise completed, all of the then calls will the timeout. So that is the console log from the then. Only then, once all of the thenables completed, will the set timeout be called. Will the next task in our, this should say task queue, in our task queue will be put back into the stack. So what that means is that promises get priority over all other asynchronous operations. If you're doing mouse events, if you're doing network requests that are not promises, timeouts, whatever, request animation frames, promises will get priority. And not only will they get priority, the entire thenable chain, the entire callback chain from the promise, if it's then or catch, will be guaranteed execution before anything else happens. Because the jobs are processed at the end of the stack. not at the next frame of execution. So if you think of the synchronous call stack, think of a little extra, and that is why it's placed at the bottom. Think of a little extra for the jobs, for the promises that are completed right after we empty out. So after the console log is completed, we check, do we have any promises to resolve? And only when that is done and all the thens are executed, do we go to the task queue, to the set timeouts, to any other asynchronous operation that we're trying to do. And that might seem like a very small detail, but what it gives us is a way of predictably and cleverly engineering the asynchronous operations that take part in our application, even if they are spread out across multiple places. Of course, promises are passed around. They are moved, they are returned from functions, and then we can then on them again. And what that does, it gives us an interface of reasoning about the order of operations of all of these callbacks within a promise. And we can do some really clever things, and this is really what I want to talk to you about. So it's in the current frame of execution and before the next one, and all of the thens are chained, and you're guaranteed chained execution. So going back to DataLoader and to the problems that we had with GraphQL, the problem really was here, that when we look at a user and we talk about friends or events, we need to deal with each friend separately because we don't have an interface of saying, oh, I'm calling this function again from another promise. They're completely detached because it's within a loop. There's no way of keeping track of the previous function because the context is isolated. So what can we do? If we look at the promise chain and the depth of our graph, we can sort of slice the graph into 4 different chunks. The first tier is the user. That's the first task that and it has nothing to do with the task queue. It's just the first task that we complete with the database. We query for the user. That's the first thing. Once we have the user, we're looking for events and the friends. That is the next thing we have to do. That is the second tier of the graph. After that, we're looking for the creators of these events and the events that my friends are attending. That is the third tier of the graph. And the fourth and the deepest one is the creator of each event of each one of my friends. So 3 levels deep. How can we somehow provide a very clean interface to try it and at least merge some of these queries into batched operations? So the solution to all our problems is DataLoader. And DataLoader, now that we understand this interplay between promises and other asynchronous operations, becomes a very simple concept. And now we can talk about what it is. It's a library. You call a new instance of DataLoader, and you pass it a function. That function accepts keys or IDs, and it returns back a promise to a resolution of those IDs. That might sound like a mouthful, but all it means is that I create an instance of a loader, and eventually that loader will call a function, it will pass a bunch of IDs, and it will expect that some kind of network request will resolve a promise that will resolve to an array with all of these models, or all of these instances or items or objects. So I'm calling promise.all, batch get users, and I'm just mapping these from an object. But I'm returning a promise that will resolve to an array with users by the order of these IDs. Now, how can we use this? What does DataLoader actually provide us in terms of our operation with GraphQL? I go into each one of my resolutions here, and instead of just fetching, I load. I just replace it with a call to the loader, saying load ID number 1, ID number 2. Now, these calls are synchronous. Let's say that I return a list of events, and I iterate over each one, and now the graph resolves every single event, and it's calling resolve the creator. These are all synchronous. They're part of the same call stack once a promise is resolved. We're calling ID number 1. It could be a for each. It could be whatever loop, whatever implementation details, but it happens within the same context. So we call 1, 2, 3, 4, 5, and we're not actually making requests. We're just calling this mysterious load function, and we're calling it for every single ID that we need from that nested response. Like we saw, if we have a big array of friends and we want the events, we're calling every single event separately. Now we load them, and we don't know what's going on yet. But we're passing them an ID, and we expect back a promise, just like a fetch. We expect a promise that resolves to just that individual object, because we don't want to mess around with our structure of the schema with GraphQL. We don't want to hack around it, because it's already complicated enough. And this is really the core of DataLoader, and I know it's a bit of an ambiguous function, but let's think about what we've just learned from promises and other types of asynchronous operations. Let's say that within the context of the DataLoader library, there's a promise, and it's nothing yet, it's just a variable called resolved promise. And when this function is called in queue post promise job, if the promise doesn't exist, it creates an immediately resolved promise. And we know that means that once the synchronous operation completes, all of the venables of these promise will run. And now we say for that promise, for every time this is called, please queue a then call on that promise. And in the next tick, once that then is completed, call a set timeout with the callback. I know that sounds, again, like a bit of a mouthful, but basically what happens here is we say we artificially create a promise, and every time we load an ID, we add a then to that promise. This is what happens internally inside DataLoader, and we load 1 and 2 and 3 and 4 and 5. And only once that promise is done at the end, call set timeout, and within set timeout, call the callback. Now the callback here would be the fetching of the users. And what that means is that I can iterate through my graph and call load 1, load 2, load 3, load 4, load 5, and they will all be called synchronously, and then all of the thens will be resolved. And the set timeout has to wait. It's in a separate queue. And the set timeout is what contains my actual database query. So I'm loading 1, and it's added to the list. 2, and it's added to the list. 3, and it's added to the list. 4, 5, 6, and I can coalesce or collect or merge all of these seemingly separate IDs of events, 1 and 2 and 3 and 4 and 5, and they're all put into DataLoader. And only once the promise completely resolved and all of the queuing then have been completely exhausted from my microtask queue will the callback from the timeout be called. And that is the one that will call the function that expects keys and returns a promise for multiple objects. It means that I'm able, from different calls in different functions within my application, collect all of these IDs and batch them into a single database request in a very transparent interface. All I had to do was initialize this DataLoader instance, pass it a function that will get all of the keys that I'm loading elsewhere in my application, and batch all of them into a single database call. So yeah, I'm essentially creating a big block like the friends from these events. I don't have to treat each one as a separate database call. And when we look at a very simplistic example of how we can use DataLoader, just so we understand it better and we can actually see the code, let's say that I'm creating a new loader now that gets user again. I create the loader here. It's a new DataLoader that gets keys, returns a promise of all of my users. And there's a function here called getUser. I'm expecting this function to be called, as far as I'm concerned, this is what is called after I'm fetching a user. So I want the then, if it's a fetch or a load or just get from server, whatever the function is named, to be called with a single user. And then I'm calling loader load 1 and 2 and 1 and 3 again. And we'll talk about caching in a second. It's 1 and 2. The individual users here are 1 and 2 and 3, but I'm making 4 calls, and I'm calling then on each one of them. We saw that internally there's a promise here, and it gets then with every single load call. That means that I'm creating this group, this record of all of the IDs that I'm loading, and only then, once I collected all of these IDs, even though they are synchronous calls, so they're supposedly in different stacks of execution, in different frames of execution on the stack, only then, once I collected all of these IDs, will they be called in batch through the loader callback. And then, with some clever management from internals of the API, I'll get every ID I asked for in an individual promise. And that's not the complicated part of it. They're just splitting the array into multiple instances and returning each one that I asked for. Now, the other powerful feature of having a queue of all of the IDs I'm about to query before I query is that I say, oh, I have a queue here of 1, 2, and 1, and 3. Why should I query for 1 twice? If I'm making all of these calls separately, it's very difficult to manage caching. I would have to have a separate manager for cache and maybe set timeouts on the queries or delay them and stagger them in a bit and see if I already have the data. In this case, I'm caching before the query ever happened. So I can see I already have one here. I'm going to get it eventually because I'm querying it here already. So here I'll just return a virtual copy of that promise, and I'll only have to make that query once. So not only are we batching, we're always optimizing to make sure that within the context of a big graph query, we only fetch for a particular asset or resource once. And I want to give you a sort of overview of how that looks like when we traverse through the graph, and we're going to finish with this sort of visualization of how we can optimize our graph. Let's say that we're querying for a user with an ID of 1. We load one, and it's placed in the loader. Now the loader will wait for the cycle to complete, and will query for user number 1. And we're still within the context of this entire query, so the loader isn't exhausted yet. We can put in the cache. And now we have user 1 ready. Now I want to query for the events and friends for that user. So let's say I go to multiple events, 1, 2, and 3, and these are my friends, IDs 2, 3, 4, and 5. So users 2, 3, 4, and 5 go in the loader sequentially, 2, 3, 4, and 5, but they're batched into a single query. And also events 1, 2, and 3. And once they are resolved, once I make these 2 queries, each loader makes only 1 query, they end up here, 1, 2, 3, 4, and 5, and 1, 2, 3. Let's say that now I want the events of each one of my friends. And they individually, we have to call this individually. Remember, we don't have that batch anymore. We're in separate processes for each one of the nodes in the graph. 1, 2, 3, 4, 5, we can still collect them with DataLoader because it's all part of a single changed promise. But we only need 4 and 5 because 1, 2, and 3 are already here. So we're utilizing the cache as well. So even though we're making just one network request, we'll only query for the missing assets. And then when I'm looking for the creator of each event, and let's say we're a very small social group, we throw up our own parties and we're the only ones attending, and it's only 5 people, 1, 2, 3, 4, and 5, they're all already here. So that's another level down the graph that you're getting completely for free. There's absolutely no network request, nothing's going to happen, and your code will still get the promises with the resolved users. And what I want to show you, and we're going to finish with that, is the ridiculous change it will make to your code just by applying DataLoader. And for me, it went from 52 to 3 queries, I think. But if we run this again, that's an absolute disaster, as we've already concluded. 35 queries, clear this thing, and let's copy the same query exactly into a GraphQL implementation that does use the loaders. We'll put this query here, it should be the same one, and run it, and we only make 3 queries. From 35 to 3, going to the first user as we've seen, then loading their friends, 2, 3, 4, and 5, loading the events, 1, 2, 3, 4, and 5 in batch, and the next call for the creator that we see here didn't even make a database call. And this is, for me, the last piece of the puzzle of fully sort of trusting GraphQL in terms of performance on top of REST, on top of custom APIs that I have full control of as a big function. So I really encourage you to explore GraphQL Relay and the connection into React, and also DataLoader on the back end to sort of understand the process that happens, even if we're only doing front end, of where the data is coming from, of the queries that you're writing. If you find yourself working on a GraphQL project, you will be the ones responsible for writing actual queries, even if you're doing front end. So I think it's very important to understand where this data is coming from. I hope that was a good insight into the world of GraphQL and optimization. Yes, thank you very much.